Hi everyone, welcome to AI Crack channel. This is Akash Kingwar and today we'll be studying methods of differentiation lecture 1. Now since we have completed differentiability and all those topics, so this is just the continuation of it. This is our question number 20 for the day and take the screenshot and let's start with the recap. So basically we studied about the basics of differentiation. We studied about first principle of differentiability. We studied about rules, basically quotient rule, product rule, chain rule, all these things. And we kind of know that there can be certain kind of functions in which we cannot just apply quotient rule or product rule and get the answer. There can be some complicated functions where we need advanced methods. So we'll be studying those methods in these lectures. So with that recap, I'll be starting with logarithmic differentiation. So basically, whenever you see this kind of, let me change the pen color. So, so basically, whenever you are seeing this kind of function, exponential function, basically one function is to per another function, and product function, multiple products, basically not just two products, multiple products, or you can see in the denominator part as well, products in numerator and products in denominator. In that case, you might have to apply logarithmic differentiation. It's not that you'll always have to apply, because in some cases you can easily simplify the functions, but in most of the cases you'll have to apply logarithmic differentiation. So basically, just to simplify, to make it more convenient, the differentiation process, we are applying this logarithmic differentiation. Now let's look at this example. Find the derivative of root x multiplied by x plus 4 raised power 3 by 2 divided by 4x minus 3 raised power 4 by 3. Now you can clearly see that this is a function which is involving product and division as well. So basically we'll have to apply product rule and as well as quotient rule. And also there are powers of 3 by 2, 4 by 3. We can see that it's not easily reducible. So basically we cannot simplify it further. So the only method to apply over here is logarithmic differentiation. So let's apply the function, that is root x plus 4 raised power 3 by 2 divided by 4x minus 3 raised power 4 by 3. Now let's take ln both sides, ln y, that would give me ln root x plus ln x plus 4 raised power 3 by 2 minus ln 4x minus 3 raised power 4 by 3. Now let's simplify it further. We'll be getting ln y equals to, the power comes out over here, that would give me 1 by 2 ln x plus 3 by 2 ln x plus 4 minus 4 by 3 ln 4x minus 3. Now this looks very simple. So now let's try to differentiate it once. So we'll be getting y 1 by y dot y dash, because chain rule. If it was x over here, then it would have been simply 1 by x. But since it's ln y, 1 by y dot y dash, that would give me 1 by 2x plus 3 by 2 x plus 4 minus 4 by 3 times 4x minus 3 dot 4, because of the chain rule. Right, over here it was just 1, it was also just 1, but over here it's 4x minus 3, so that's why 4 over here multiplied by 4. So this is our final function, and y dash would be y times basically the function itself. So that would give me root x plus 4 raised power 3 by 2 divided by 4x minus 3 raised power 4 by 3 multiplied by 1 by 2x plus 3 by 2 times x plus 4 minus 16 times 3 times 4x minus 3. So this is the final answer. If you would have tried it, doing it with the help of basic methods, then probably would have screwed somewhere over here and you might have made mistake. So that's why logarithmic differentiation should be used carefully. Now let's look at this example. Y equals to 1 plus x raised power 1 by 4 dot 1 plus x raised power 1 by 2 dot 1 minus x raised power 1 by 4. And we have to find the derivative. So the first visual thought after looking at this question is we have to apply logarithmic differentiation. But the problem is we can clearly see that over here, that it can be reduced. We see 1 minus x raised power 1 by 4. We see 1 plus x raised power 1 by 4. So that triggers a square minus b square in my mind. So basically I'll be clubbing both these functions. So that would give me, so basically the main idea was just don't apply logarithmic differentiation when you see a multiplicative function, because you have been told. But first try to simplify it further. If it's not able to simplify it further, then probably you can apply logarithmic differentiation. So this would give me 1 minus x raised power 1 by 2 if we club both of these, then we'll be getting 1 minus x raised power 1 by 2 multiplied by 1 plus x raised power 1 by 2. Again, we can club both of them. That would give me 1 minus x only. So dy by dx would be nothing but only 1 minus 1, right? So that become fairly simple. That became fairly simple. Now let's look at this example. We have to find differentiation of y equals to x raised power x. Now this is also a standard question. So basically you'll have to remember it. When you, whatever the kind of conclusion or the derivation you are going to get from here, you'll have to remember it. So basically y equals to x raised power x, and you can see that it's not further reducible or simplified. So basically you'll have to apply logarithmic differentiation. Ln y would give me x times ln x. So basically 1 by y dot, 1 by y dot y dash, that would give me x times 1 by x plus basically product rule multiplied plus ln x dot 1. So that would give me y dash equals to y times x 1 plus ln x. So this you have to remember it. So y dash equals to x raised power x 1 plus ln x. So just remember this for this function. Now let's talk about differentiation of implicit functions. Now what do we mean by implicit functions? You can read on this entire theory afterwards, but let me explain you implicit and explicit functions in a simpler manner. So let's say we have a function y equals to ax square plus bx plus c, basically a simple quadratic equation. Now I can clearly say that y is a function of x and nothing else, right? But let's say I have a function y equals to axy plus bx square y cube plus cy, or maybe cy raised power 4. In that case, I cannot really say that y is just a function of fx. I cannot say that, right? Because it's also including multiplication of y or y cube or y by 4, and we cannot really separate these terms out, right? We cannot just write y in terms of x because it's not humanly possible with our limited knowledge that we can separate these terms out. So this equation or this function is called implicit functions, and this is called explicit, basically explicitly expressing in terms of x, right? So for differentiating these equations or functions, what we do, we just differentiate both the sides and try to separate out the y dash terms and find the final value. This is how we do. Now let's look at one standard example for the same. Let's say we have y equals to x plus 1 upon x plus 1 upon x plus 1 upon x plus till infinity. Now I can see one pattern over here is that, let's say if I hide out this term, then this is also y because it's going till infinity. This entire term is also going to infinity. If we just hide out one term, then also it's going to infinity. So basically I can write y equals to x plus 1 by y. Now let's cross multiply it. We'll be getting y square equals to xy plus 1. So let's try to differentiate both sides. We'll be getting 2y dot y dash equals to x dot y dash plus y dot 1 plus 0, right? So if I try to separate out the y dash terms, what I'll be getting, y dash 2y minus x equals to y. So basically y dash equals to y upon 2y minus x. So this is our final conclusion, that y dash is this. So this is how we have to do in every single question. Sometimes we'll have to plug in the value of y once again to find out certain values. So let's say over here we are not plugging it back. Sometimes we'll have to do it to find out something. So that way, these are the only two formats you can get questions in: implicit or explicit differentiation. Now let's solve one more question. And just a point before solving further, whenever you're solving any question of differentiation, try to simplify it further if it's in the possible domain. Sometimes it might not be in domain to simplify it further because that might change the function itself, but it's permissible in domain, then try to simplify it first and then differentiate it. That would be the ideal scenario to apply any method. So over here we have been given one implicit equation, that is x plus 1 under root 1 plus y times 1 plus x equals to 0. And whenever I see something under root and we have to differentiate it, I just don't want to do it. So what I'll be doing, I'll be squaring it both sides. Let's try to do it on the next page. X times 1 plus y, x times under root 1 plus y equals to minus y times 1 plus x. So I'll be squaring it both sides. So what I'll be getting, x square 1 plus y equals to y square 1 plus x. X square plus x square y equals to y square plus y square x. Or probably just don't multiply it and we'll just, differentiate it directly. So over here we can apply product rule, over here we can apply product rule. So that will give us 2x dot 1 plus y plus y dash dot x square equals to 2y dot y dash times 1 plus x plus 1 times y square, right? So this is the differentiation of both sides, and we just have to separate out the y dash terms. So basically we have got 2x plus 2xy plus y dash x square equals to 2y dash times 1 plus x plus y square. So you can do the calculation of doing all this stuff. So this is just the method to explain you how to do these things, right? Now let's talk about differentiation of inverse function. So let's say we have a function y equals to ax plus b. Now I can clearly see that over here, if we have to find out inverse function, that would be y minus b divided by a equals to x. Replace y with x, that would be x minus b divided by a equals to y. So this is our inverse function, and we can easily find out the derivative of this inverse function. But let's say we have a case y equals to ax square plus bx plus, let's say, sin x. So over here we cannot really find out the inverse of this function. In that case, how would we find out the derivative of the inverse function? So there has to be some method to find out the derivative of the inverse function. So we'll be studying that over here. This is the standard case, but that might not be asked in examinations. These kind of questions can be asked in examination. So let's see. So let's say there are two functions, g function and f function, and gx is inverse of fx. So we know one property, that if g is inverse of f, then that would be x. G of fx would be x, right? And the opposite is also true. F of gx is also x, right? That is the property. Now let's try to differentiate it both sides. That would give me g dash fx dot f dash x equals to 1. So g dash fx equals to 1 by f dash x. Now this gives me something. Now let's say we want to find out, let's say g dash of a. So we'll find out the x value for which this function becomes a, and we'll plug in that x value over here and find out the differentiation of g dash a, right? So this is the method we have to utilize in the actual questions, not the standard one. Let's take one example. Fx equals to x cube plus x5, and g is the inverse of f. Find g dash 2. So this is a very standard problem. Let's see how we do it. So we'll write once again g dash fx equals to x, and g dash of fx dot f dash x, that would be 1. So basically g dash fx equals to 1 upon f dash x. Now we have to find g dash 2. So basically we have to put 2 over here. So basically fx has to be 2. Sorry, fx equals to 2. Now we can clearly see that fx equals to 2 for x equals to 1. For x equals to 1, fx equals to 2, and we are plugging it over here. So basically we have to plug x over here. X equals to 1 over here. So g dash 2 would be 1 upon f dash 1. So f dash 1 would be f dash x equals to 3x square plus 5x, sorry, raised per 4. So if we just plug in 1 over here, that would give me 3 plus 5, that is 8. So that would give me 1 by 8 as the answer. So this is how you have to do in all these questions. This is a very standard question. This is a very standard method. And around this method only, if at all, you'll be getting questions in PGDBA, right? So this was it for today's lecture. And tomorrow we'll be continuing with the MOD lecture 2. And with that, we'll be finishing differentiability, methods of differentiation, basically everything about differentiation. So let's catch up tomorrow. Thanks for watching.